I would be your host today for showing you what's new in SolidCAM 5-axis simultaneous. There are some nice improvements in the, if you look at what's offered on the plate today, there are a lot of new things in SolidCAM 5-axis milling. Also, there are some very nice improvements in the earlier functions of SolidCAM 5-axis milling. But what's more exciting are the new functions that are developed by SolidCAM for specific area of 5-axis application. Today we are going to see both of them. Let's first start with what we already had and what are the improvements in the areas that we already have. The first improvement that we see is that we have now added a retract feed rate that you can now define in all simultaneous 5-axis operations. Earlier the retract was directly a G00 function. Now it's added as a feed. You can define that as feed. You also have an option now to fit arcs in your rapid moves, whether they go to the clearance area or the retract distance or to the safety distance. You have an option to fit that. You also have an option now to define a different safety distance while entering a job and a different safety distance while exiting a job. Also, there are some very nice improvements for controlling the step angle in rapid moves. I'd like to show you a part where I can show you both these areas. Okay, let me open. Yep. So I have this part with me. Let me edit it. And in the levels, we have got this option: entry safety distance and exit safety distance. Currently, by default, it's set to 2. So if you look at the simulation now, and if I zoom into that area, you can see that the safety distance is set to only 2 millimeter, whether it's entering a job or exiting a job. So you can see that safety distance is set to 2. Now these two values can be changed in the new version. For example, I can have 25 as my entry safety distance and exit safety distance as only 5 mm. If I calculate this and run the simulation, you can see that I have 25 millimeters as my entry safety distance and only 5 millimeter as my exit safety distance. You could reverse it, but this is a pretty new function that has come in. The other function that we just talked about was putting up the arcs for rapid moves. So if I now apply a depth cut, or let's use a depth cut, 2 and 10. Okay, let's save and calculate. So we have now a depth cut. And you can see that we now have the arc fit in the rapid move. Where is this found? This is found in the levels page, and we have fit an arc out here. If I remove this and calculate, this is what it used to look like in the earlier version. But in the new version, you have a possibility to define an arc radius, let's say 25 millimeter. And we calculate the toolpath, and we get this nice arc out here, so that the the rapid moves are pretty smoothened out. Okay, let's move back again to our presentation and see what's new again. You also have a control of toolpath behavior in case of collision. I'm going to show this particular feature because it's going to be very clear when I show that part. I'll show this particular feature when I'm doing the conversion, because it's more relevant there, which I can show it very clearly. So right now you could say that we have this feature which allows us to keep either the collisions or to trim the colliding contours and relink them again. Whether it is the cutting contours or the links, we could do both of that for each of them. And then we have some nice new tilting options. We have a new tilting option called tilt relative to contact point, and in the tilted through point, we have a new sub option, tilt angle from point towards axis. Both of them are going to be pretty useful when you're going to do your toolpath using the regular 5-axis engine. We then move to swerve machining. Now, before I go into swerve machining, I would like to show you a couple of other new changes that have come into SolidCAM. And these are more related to our leads and links. Let me first switch off the depth cuts because it's difficult otherwise. Okay. Now, if you go to the link and to the lead in, we have got three new lead in and lead out. One is a position line, the other one is a vertical profile ramp, and then you have a vertical profile, reverse vertical profile ramp. Let's first, for entry, since we are going to enter into the material, I would like to use a vertical profile ramp with a fillet radius of 3 mm and the length of the entry to be about 10 mm. And for the lead out, I would like to use a position line. Now, I would like the lead out to come from a point out here, which I have already predefined, and the direction or the vector direction of this lead out will be defined by 2 points, which I have in my sketch. That's point 1 and that is point 2. So this is going to define my, it's basically going to define my vector and the height of the lead out. Okay, let's hit save and calculate. Let's run the simulation. So what you see here first, you see a first nice entry into the material. Basically, 3 mm above, it takes the ramp into the material and then starts cutting. And when it is exiting out, it's actually going to follow the vector that I just defined. It's going to use this vector that was defined by 2 points. It's going to pull out and then go out of the job. So as far as our entry and exit goes, these are new things that are already added into the software. All right, let's close this part and let's go to our main area of 5-axis. Swerving has undergone a major change in 2013. The engine is now much more robust. I'm going to show you a few examples which will prove it. And the most important part in our 5-axis toolpaths, for example, some special applications that we have developed, which I'm going to show you today, is the amount of inputs that go into the software is bare minimum. You know, if you look at our earlier 5-axis engine, you will notice that a lot of inputs go into the software, whether it is geometry, construction, tilt lines, points, gouge check strategies, a lot of them. But when you start looking at the newer functions that are developed by SolidCAM, you will see that the inputs are bare minimum. And the best part of these toolpaths are they are ready to cut. You don't need to do any changes. They are ready to cut, gouge free, always. And the tilt control is automatic. No need for defining any kind of tilt settings. The software will handle the tilt control all by itself. First of all, under strategy you've got, there are different possibilities. You could select surfaces as your swerve geometry. You could select just an upper curve and a lower curve that defines a swerve geometry. You could define tilt lines to control it if you want to control it. It's a big if, because some people don't like to control. They just like to define the surface and they like to get the toolpath. That also is possible. You could define a flow surface in case you're doing an internal cavity so that you don't want it to go below a certain surface.
Welcome to GoToWebinar, web events made easy.
With the existing toolpath engine that we have, the amount of features or amount of functionalities that are given in tool axis control are bare minimum. This is kept in mind to make this function as simple as possible. People can start cutting immediately. A new gouge check page which can help you to degouge if there is a gouge with the swerve surface and also with certain check surfaces. You can look that there are no strategies available once it has detected gouging, because this is an automatic gouge check control. We're going to see a lot of these in the few parts that we are going to see later on. We also have corners. We have the possibility now to add corners. You could add a radius. You could add a relief groove, or you could keep the corner sharp when you're cutting in swerving. When it is for external corners, you could make it a sharp corner turn. You could curl along a radius, or you could provide a loop. Anything is possible. We have given all the options to the user. This is only if you would like to use it. By default, they're all switched off. And then we have a new short distance strategy which basically determines the tool orientation based on the ISO lines of the defined curve. So this is a new strategy that has been added to swerving. Okay, let's now get into our software and let's look at some new things that have come up. So let me open. I'll open a very simple part now first to understand what the swerving is all about. Let me delete this. Okay, so I have a part. If I now go into evaluate and run the draft angle analysis, you can see that we have got a negative draft of 8 degrees out here and a 5 degree negative draft. So there's a blend between -5 and -8. And the same thing out here. We have got a -5 and a -8. Plus, the floor is not a straight floor. It's defined on a spline. We have a fillet radius. So it's not very easy, but it's not complex either. And then we have a second pocket which has got a -8, -8, and -8 on 3 sides. And when it goes onto one side, it actually becomes positive draft of 5 degrees. So it has, this part has variations on both sides. So let's see how we can handle such parts. Okay, let me come out of the part environment and back into my SolidCAM. So let me add new swerve machining. Geometry selection, you can look at how easy it is. There are many strategies available. The by default strategy will always be set to automatic, and it works almost in every case. It's only that when you don't have surfaces, or when your surfaces are really bad and you don't want to use them, you can switch over to a different strategy. Else, the strategy works almost on 100% parts. Let's select our swerving surface. 1, 2, 3, 4, and 5. So we have 5 swerving surfaces. Okay. We also are going to define a flow surface. You can look, once I've defined my swerving surface, my upper and lower curve are blanked out because the upper and lower curve will now be determined by the software itself. So let me select the floor. The floor is this surface and also the fillet. The fillets in case of SolidCAM constitute the floor. They belong to the floor. Okay. Let's pick the tool. 12mm ball nose. Levels. I don't check anything on the levels. Toolpath parameters. The only thing is the side. I can keep the side to inside. It has to cut inside. I'm not going to touch any of the corners. Neither will I do any changes to the tool axis control unless there is a lot of rotation happening on the rotary. I'm not going to touch the tool axis control. Neither will I do any other checks. In this case, I will just hit save and calculate. If I run my simulation now, you can see that the toolpath already has been calculated. Straightforward calculation, no creation of any cutting, geometry, tilt lines, nothing. So if I now run my machine simulation, you can see how easy and nicely it is cutting. This, you run my move list, and let's go step by step. That's it. So it's pretty straightforward, no gouges. Cut using the side of the tool, I've finished the entire wall. Now there's a possibility that, let me go to the host CAD so that I can see the simulation much better. There's a possibility that you can add number of cuts here, out here. How we do that? We go into roughing and more, and I will say I want 10 slices. Now along the tool direction, I can give 10 slices. Now if I run the simulation, you can see that I've got 10 slices out here. I can also define number of slices along the material direction, which means if I have more material on the side, I don't want that material to be cut in one go. So what am I going to do? I'm going to add 3 layers, with each layer distance between each layer of 2 mm. If I hit this calculate button again, and if I run the simulation, you have got 1, 2, and 3. 3 levels, 2 mm each. Okay. Let's check the next pocket. I'll add another swerve toolpath. Geometry, swerve surface. 3, 4, 5, 6, 7, and the surface out here, 8. The flow surface, is that 1. 2, I'm going to select the 12 ball nose. I'm not going to do anything else except saying that this is going to be machined from inside. I'll hit save and calculate. It's as good as doing a 3-axis toolpath. You pick the geometry, pick the tool, check the parameters, apply, and you have a result. So if I run now the machine simulation again, let's run. You can see how nicely it is doing and it's already positioning itself to the next wall. When it's crossing the second wall, the positive wall, it's already positioning itself. That's it. Very nice. Good. Let's pick a slightly more complex part. This part, many of you would relate it. It's basically a wall of an impeller. Generally, impeller walls are not straight, but if you have an impeller with a straight wall, you could always use a swerving method to cut the wall because it's much more simpler, faster, and much more accurate. You could use the side of the tool. So let me open another file. Delete this toolpath. So I have got an impeller with surfaces out here which I would like to swerve. So let me add swerve, geometry, the swerving surface. I'll pick 1, 2, there's a small fillet in the front, 3, and then there are 2 small pieces out here, 1 and 2. I'm not going to select this surface because I will add it later to show you how easily we can edit it and add surfaces to an existing geometry. I'll pick the flow surface, 2, 3, 4, and 5. These are all my flow surfaces. Tool, I'll pick a 10 ball nose. I don't need to do anything else except, again, the side. You can set it also to auto detect. Best ways to set and define it the way you want. I will just hit save and calculate. Remember that this particular part is not a part that has been designed in SolidWorks, but it's an imported geometry. So if you look at in that context, it's a pretty complex part because it's a surface that's been imported into SolidWorks, but that doesn't deter the Swerving Engine. It creates pretty neat toolpaths. So if you now run the machine simulation, you run it step by step so that you can see it. And my point of interest would be on the front fillet, because I want the tool to roll on the front fillet and not to dance on the front fillet. And you can see that the tool is nicely rolling on the front. It's not dancing around the fillet, but it's nicely rolling on the fillet. And as it goes down, it starts becoming again normal to my bottom face, cutting the side. That's it. So we have a very nice swerve toolpath to machine the side of this impeller. Now I could include this. I could include one of the surface. So what I can do is edit, go to the geometry and edit this swerve surfaces and add this geometry to it and hit save and calculate. Don't need to do any other gouge check, nothing. It's done the toolpath. One single toolpath going on the entire periphery of this part of the blade. You could also apply the same technique that I showed you. You can have 5 slices and calculate it. If you don't want to cut the whole thing in one go, you could go step by step into the material. Okay, that's done. Let's run the simulation. So we have nice 5 passes going on the periphery of the blade. So the swerving is a pretty powerful engine. You can look at the results. I'm not defining too many things. I'm just defining the most basic elements needed for any toolpath calculation, and that's it. It's doing an excellent job in generating a 5-axis toolpath. Let's look at the slightly even more complex part for swerving. Let's open, and let's take a portion of a frame component. All right, we have something out here. You can look, the surfaces are not even, they are uneven surfaces, so we're going to use a swerving engine to generate a toolpath for one of these areas. Let's delete this. Add another swerving toolpath. In the geometry, I already have some geometry saved for me. Not that one. Let's define a new geometry. Don't need to select an existing one. So I'm going to select these geometries as my swerving geometry. Okay. And the flow surface as the planar flow and the fillets together. All right, let's say OK. Let's define the tool, 12mm ball nose, toolpath parameter inside. OK, I don't need to do anything else. Hit save and calculate. Done. Let's run the simulation, and let's run a simple HostCAD simulation to understand how it's working. You can see it's pretty smart. What it is doing is, once it starts moving towards a particular wall, it starts orienting itself to that wall's draft angle. So now it's going on to become almost straight because the wall that it is approaching is straight. But when you look at this view, it is still having a draft. It's doing the undercut milling, but it already knows that it is approaching another wall, so it's tilting itself to that other wall, but it is keeping the tilt of the other surface constant while it is changing the lag angle. Now it's going to have straight approach. It's going to be almost straight on both sides, but now it's approaching another wall which is having a negative draft. So as it approaches, you can see that it is already changing its lag angle again. It's changing the lag in such a way that it doesn't need to do any kind of major transition at the fillet. At the fillet, it's only going to do a very minor transition, and it's back to the wall. Now you can see as it starts moving to this wall, which has got a great positive draft, it starts changing its position again. And as it comes closer to that wall, it's already taken that position so that the changes on the fillet are bare minimum. Because generally when softwares tend to change on the fillet, I tend to eat away material from the fillet because the machine has a certain degree of acceleration and deceleration. Generally, some machines can't take it, so they tend to dig into the corner. Okay. And as it again comes back to this face, it's changed its lead lag, made it straight, and now it retracts out. Simple. You can see the most complex of the areas, the toolpath is generated really very quickly with bare minimum inputs. You don't need, not much of an inputs are gone into deciding or defining this toolpath. Right. So this was about swerving. The same swerve can be done even with two curves, the upper curve and the lower curve. You don't need to define the surface. But if you have the surface, the software's priority is always to the surface first. It tries to determine the upper and lower edges by itself when you define the surface. All right, let's move, close this part, and move to another very exciting area. I call this exciting because this has been pending from a very, very long time, and there are hardly any softwares today in the world that can handle these kind of parts so effortlessly. I'm talking about what we call as the multi-blade parts, or parts for impeller. We developed this very powerful engine for machining impellers and discs, what we call as the multi-blade application. The classic application for this, I would say a classic part for this kind of an application is impeller with splitters. It could be 1, 2, 3, 4 splitters, it doesn't matter. Minimum input is needed. Again, just like swerving, you have only minimum input that needs to be given to the software. The tool axis control is controlled automatically. The biggest problems in machining impellers are always the root fillets. The moment you have root fillets, you get into major issues because of the tool axis control. However, in our new technology of multi-blade machining, the root fillets are handled with ease. And we have separate strategies for roughing, blade finishing, fillet finishing, and hub finishing. We're going to see all of these on a couple of parts today. First of all, we need to understand that there is a new area for technology where we define roughing, blade finishing, hub finishing, and fillet finishing. Everything will be done in a single operation, or you could have different operations for different blades. So you have got the following strategies: the root finishing, roughing, blade finishing, hub finishing. And for each of these strategies, you can use different cutting strategies. For example, you could have parallel to shroud, parallel to hub, or you could morph between shroud and hub. Now, what are these elements? Basically, if you look at a multi-blade impeller, you have got number 1, which is the hub surface, number 2, which is the blade surface, number 3, what we call as the leading edge of an impeller. Number 4 is the trailing edge of an impeller. 5 is the root fillet. This is the most trickiest part in any impeller. Number 6 is the splitter itself, and number 7 is the shroud. So these are the elements of blade. Rather than going into a presentation now, I'd like to take you directly into the part so that it's much more exciting. Let me open a multi-blade part. And delete all the existing tool parts. I don't need them. We will see how to generate tool parts for this particular part. Right, so let's add multi-blade machining, roughing. Let's start with roughing. In the geometry, I first need to decide what kind of a strategy I'm going to use. So the most commonly used strategy is offset between hub and shroud. So I'm going to use that, hub and shroud. And now it's asking me to define the geometries. Now the geometries are split into 3. The first geometry that I need to pick is the blade surface, splitter surface, and the fillets. Everything as one. So this is what I'm going to do. I already have the surface picked. So let me see this. Yes, these are the surfaces. I have these surfaces. You can see that blade surface, the fillets, the shroud, everything is picked in one go. So I'm going to have this as my blade, splitter, and fillets. I would like to keep an offset of 0.35 millimeter on all of these surfaces. The hub surface, in fact, can be just a small segment out next to the blade. You need not select the entire hub, like what I'm going to do now here. I have selected only a portion of the hub here. Although I'm going to machine on this side, I don't need the hub always to be near the blade. It could be on the other side of the blade. It doesn't matter. The software is very intelligent. It knows what you're trying to pick. So when I pick this as a hub surface, it realizes that you have picked up a hub, and it revolves this hub around the entire blade. So I'm going to keep another offset of 0.35 on this hub. And now since we are going to do a morphing between hub and shroud, I would need to pick the shroud. The shroud is this. I don't need to again pick all the surface. I just need to pick only one of them. Again, software is pretty intelligent, understands everything. So this is my shroud. Let me pick a taper ball nose. I'm picking this cutter. It's a 12 millimeter taper ball nose. Generally, taper ball nose cutters are very, very commonly used for machining impellers because they are pretty rigid. Even though the corner radius is small, the shank is pretty rigid, so they tend to give better cutting results. Let's select. You can see that in levels, it's auto. It's auto detect. I don't need to define anything out here. It's auto detect. The software knows what it is trying to do. In the toolpath parameters, I only need to define how many number of depths I need and how many cuts I need in between them, in between the blades. So I'm going to define 10 cuts and 10 cuts between the blades. So step over, I need 10 cuts, and on the depth side, I need 10 cuts. In the surface quality, I would like to increase the tolerance because the tolerance is, it's not needed so tight. Sorting, I'm going to make a zigzag starting from the leading edge. The leading edge is this edge out here. This is the trailing edge, and this is the leading edge. Okay. Tool axis control, I don't need to do anything. Link, automatic, I don't need to do anything. Gouge check, not needed because on the surfaces that we have selected, the gouge check is automatically built in. Roughing, we don't need because it's already defined. I don't need to cut the stock because I'm going to go offset from shroud to hub. Up to shroud is already turned. Well, that's it. I'll just save this toolpath and I'll hit calculate. It would take about a minute, less than a minute, to calculate this tool path. All right, it's done the calculation. Let's look how the tool path looks like now. If I simulate this, very nice. You can see the connections. They've been connected using a blending of a spline. Each layer is connected using a spline that's blended between the passes. And now if I run the Solid Verify to just show you how the cutting simulation looks like, I'm going to switch off the fixture as well as the holder and run the simulation. On your screens it could be a bit jagged simulation, but trust me, it's doing a neat job. Absolutely smooth rotary changes, smooth tilting. Okay. So it's kept about 0.35 material on the sides, which is what I have asked it to keep, and it continues to rough down. We can see an image of this rough down later because it's going to take a couple of minutes more and we have a lot of things to cover. Right, so I'm going to pause the simulation and come out of it. Right, so what I'm going to do now is, since I've done my roughing, I can use the transformation and rotate it to the other blades that's already there inside SolidCAM. But the new thing about the transformation is I don't have to, if I go to the roughing and more and go into the rotation axis is automatically determined by SolidCAM, and I just need to key in the number of segments. The moment I key in the number of segments, SolidCAM then calculates the angle between the segments and distributes the transformation equally. So it's almost automatic inside SolidCAM for this particular function. Okay. My next task is to finish the blade surface for the main blade as well as a splitter. So I'm going to add another multi-blade machining option. Let me go into my browse, and I have got only the blade surface is selected as one of the geometry. Okay. Hub, I already have it. That's somewhere on the other side, but that doesn't matter for the new function. It could be anywhere on the part. And since I'm also going to be doing a morph between hub and shroud, I would also like to pick the shroud. Okay. I'll use the same tool, a taper ball nose. Levels, automatic, and in the toolpath parameters, I'll need about 15 cuts. And my start is not going to be exactly on the edge, but I'm going to go 5% below the exact edge so that I get a very neat cut and I don't have any issues. Oh, sorry, this is the blade finishing. I picked up the roughing by mistake. Okay, the hub is here, and this is the shroud. Okay, tool is the same. The contour here is not full because if I say full, it's going to do complete the entire blade, including this surface, which I've not selected. So I don't want the entire thing to be done. What I want is that the toolpath should be trimmed at the trailing edge. So I will select the option, trim trailing edge. I have 15 passes. The upper pass is going to be 5% below. 10 microns is my finishing tolerance. It's going to be one way, always, because it's a climb milling. All right, In tool axis, again, I don't need to define anything. You can see that I'm not touching any other area. I can just hitting save and calculate. Okay, that's done. Let's look at our simulation. Not this. Let's go into the host CAD. And you can see that it's created a pretty neat toolpath. Now if we run the machine simulation, it's doing a very nice cut. Okay, so I'm done with the finishing of the blade. Very easy creation of toolpath. I would now like to focus my attention on the splitter, so I'm going to save and copy this operation, and in the geometry I'm just going to change this to the splitter geometry. I'm just going to change to the splitter geometry, not doing anything else, just hit save and calculate. Run the simulation, and I have a very neat toolpath even here on the splitter. Perfect. Now we have done the blade and the splitter. I need to finish the fillets of both the blade and the splitter. Again, a simple operation, no much input needed. You'll notice I'll add multiblade, fillet finishing. I just need to select the main surfaces, so it's faces 3. These are the faces that I just selected, only for the single blade.
Welcome to GoToWebinar, Web Events Made Easy.
Toolpath parameters. I'll take about 8 cuts on the blade and 5 cuts on the hub with a step over of 0.5 or 0.3 between each of them. And I'm going to trim on the trailing edge. I don't need to do anything else. Simply hit save and calculate. This will take approximately a minute, each of these operations, because it's not an easy operation. You look at the inputs that have gone into generating the toolpath, a bare minimum basically. All right, that's done. Let's look at the toolpath. Very neat toolpath for the fillet. That would finish off the fillet. Right. I'm going to save and copy. And the geometry, again, I'm going to pick the splitter because I want to finish for the splitter now. And hit save and copy. Save and calculate, sorry. All right, that's pretty quick. We've also finished machining the splitter fillet. So it'll give us a nice fillet at the bottom, nice merging. Once I've done the fillets, what now remains is cutting the hub itself. So let's add another multi-blade operation. Let's go to hub finishing. In the geometry, I need to select the entire 2 main blades and 1 splitter, which already I have, and the hub itself. Again, the hub need not be here. It could be somewhere else. It doesn't matter as long as you have the hub surface. I've selected the hub. I would like to keep about 0.15 away from the blades because they are already finished. I just want to finish the hub. The tool, 12 millimeter taper mill. Again, I would like to have about 18 cuts on the hub, and it's going to be zigzag starting from the leading edge. And we can go left to right, we can go right to left, we can go center away climb and center away conventional. So let's go left to right. No other things needed, just hit save and calculate again. Right, that's also done. Let's run and see how the toolpath looks like. That's also nicely done. Let's run the machine simulation to see how this toolpath looks like on the machine. It looks pretty good. Let's run one by one. Okay, that's only for the first pass since it's bringing it out. Otherwise, it's going to be pretty much smooth. Right, so this is how we would finish impeller, right from roughing to finishing. You saw it's pretty easy to cut this part in SolidCAM. Now, this part looks pretty clean. Honestly, it has got clean surfaces, but what happens if we have an imported geometry? Does the software behave the same way on an imported geometry? We're going to see this on another part. Basically, this actually is a customer part. So I'm going to pick this part. Let's do a couple of operations on this so it will be very clear on how this part looks like. I'm going to remove this toolpaths. Okay. You can look, the part doesn't look that great. The surfaces are all broken up. The fillet there is a pretty complex one. It is running all around the blade, and it's basically a variable fillet. So this has got all the ingredients of a complex multi-blade impeller. Let's check how SolidCAM would handle this. Right, let's add multi-blade machining, roughing. Let's check if we have the geometry already. Okay, I think we do have the geometry here. Yes, we have the geometry here, faces, which is basically the area that we are going to machine. Okay, this is our blade, splitter, and fillets. I would like to keep about 0.35 again on this. On the hub surface, which is faces 1, you can see I've just selected a portion of the hub. I don't need to select the entire hub here. I just have selected a portion of the hub. The other things, the software knows how to handle it. Let's say okay, I would like to keep 0.35 on this also. And since we're going to go between hub and shroud, I also would like to have the shroud, which is this face. All right. The tool that we're going to use again is a taper ball nose end mill. And we have 10 passes again on the depth wise, and across we have got 10 passes. Let's give 50 micron tolerance to this cutting. And sorting, I would like to go zigzag starting from the leading edge. Okay. I don't need to define anything. Again, everything is bare minimum in this. Let me save this operation and hit the calculate button. Remember that this is an imported geometry, so this could take anywhere between 1.5 minutes to calculate the entire toolpath, which is still quick considering the kind of inputs that we are giving to the software. And this is pretty unique because it's almost like a one-button programming, very rarely seen in softwares worldwide. SolidCAM is going to be one of the rare breed softwares where you're going to have these functions so automized and so reliable. You could also look at the speed of calculation. On such imported geometries, calculating at this speed is really amazing. It's already done the roughing. Let's run the simulation. That's it. It's already calculated a very nice tool path to cut the impeller in roughing. Perfect. Right. Now, let's do the finishing. Let's see how the finishing comes up. So let's add. In fact, I don't want to do the finishing on this blade. I would like to do it on some other blade. That's also possible because you don't need to have the same surface repeated. Let's go offset between hub and shroud. Let's pick maybe a different set of surface, not this one. Yeah, this one. Let's pick this surface. The hub surface could remain still the same, and the shroud could also remain the same. Yep. Let's pick the tool, 12 millimeter, and I would like to have, sorry, again I made a mistake. Let's go to blade finishing. Have, what was that? Faces 6. The hub is faces 1, and the shroud is face 2. Okay, tool is done in the parameters. Now since we have selected the entire geometry out here, I don't have to trim this tool path on the trailing or leading edges. I can ask for a full tool path, 12 passes, and the upper pass again I would like to have 5% below the exact edge. Surface quality, let's increase the tolerance a bit. And in the sorting, I would like to have a spiral starting from a leading edge. Climb, that's all. I don't need anything else to be defined. Let's save this operation and calculate. You can look how quick it is in calculating. It's running the slices now. And once the slices are run, it will run two engines. It will run the spiraling engine, and it will also run the collision engine, the collision check engine. So both this together, all the three things put together, should take anywhere between 45 seconds to 1 minute. It's already done. Let's run the simulation. And this is our toolpath. Very quickly it has generated an excellent toolpath. Don't worry about the fillet, because the fillet, remember, will be finished later on using the fillet finishing strategy. All right, let's copy this operation and paste it. And what I'm going to do here is change to only the splitter. Let's find out the splitter geometry. Yep, the splitter geometry is this. Don't need to do anything, just hit save and calculate. In this particular case, I would like to show you a very nice thing about gouge check of SolidCAM. Because generally when you get gouges, the user really has to break his head to find out what he has to do now once the gouge has been detected. Now this becomes very tricky. So let's run the simulation. The toolpath looks okay, but let's go to the machine simulation and we'll probably see a gouge here. Right, let's quickly run the simulation. I'm going to increase the speed. You might not see it on the screen. Okay, so what it has found is, as expected, it's found collision between the part and the tool table, tool arbor. Right. So how do we handle this collision now? Simple. I'll go to gouge check and I'll select the gouge check with the check surfaces. I want the software to check for this surface, and this surface. Okay. I will give a 0.5 millimeter tolerance and I'll simply hit calculate. What it is going to do inside the gouge is left to the software. I just want that it keep away from these surfaces by 0.5 millimeter. It's pretty smart when it comes to what it is going to do now. It's going to use a combination of moving tool away and tilting and lead lag angle to give me a acceptable result. Let's run the machine simulation again. We have the tool path. Let's quickly run the simulation. Absolutely no gouges. So you can see how it handled this area out here. It's pretty tricky. It changed the lead lag and moved the tool away from that surface. So it has worked. I just had to select the check surface and I'd select how much I want to be away from this check surface. The gouge check is already done. Perfect. Let's now also finish off maybe one of the surface. Let's do the fillet finishing. So I'll add multi-blade and fillet finishing geometry. Let's pick the long blade of that one. Oh, not even that one. I'd like to finish this one. Yeah. 6. All I need to figure out is the hub now. That's selected. And I need to define which tool I'm going to use, taper mill. And on the blade side, I would like to have 8 cuts, and on the hub side, I would like to have 5 cuts. 0.5 between them, the spacing between the cuts. Okay, I'd like to start at the trailing edge. Immediately just hit save and calculate. As I said, it will take about, again, a minute, not more. Done. Let's run the simulation. Of course, not machine simulation, but yes, you could also run the machine simulation, but better than that is the host CAD. I'd like to show you the tool path. You can see how neat and clean the tool path is on the fillets. It's machined the entire fillet. Nice merging to the hub, nice merging onto the blade. So you can see that the software works very well even on imported geometries. It's not that your geometry has to be perfect. You could have also an imported part, a complex part. By the way, this impeller is not a straightforward impeller. It's a complex impeller with splitter, and you can see how easy the results were created on this particular impeller. Right, so let's do a quick wrap-up of Multiblade. So we have this roughing. In each of the strategies that you've seen right from Swerve into Multiblade, you could see that the whole thing is being done using just 4 or 5 steps. Selection of strategy, geometry selection, tool selection, side step and depth selection, and hit calculate. That's it. You have the tool path. You don't need to break your head on anything else. No other construction geometry, no tilting curves, no tilting melting contours, no points, nothing. So each of these strategies, starting from roughing, and that was the result, by the way, of roughing, and that's how the end result of roughing looks like, to blade finishing, 5 steps, fillet finishing, just 4 steps, hub finishing, 4 steps. So you take any of these strategies, any of these technologies, you don't need to define not more than 4 to 5 steps, which is a major breakthrough in toolpath calculation. You don't have to really spend hours and hours together breaking your head on what to do next or how to do next. What geometries you have to create, what curves you have to create, what will I do if I get a gouge. Everything is now done almost automatically by SolidCAM. Right. That was with our multi-blade. Let's enter another very exciting area of port machining. A very robust engine, very powerful engine for machining ports. It has got a similar technology of what you saw in Swerve and multi-blade, which means very bare minimum inputs are needed. You don't need more inputs. The tool axis control is automatic. And there are separate strategies for roughing, the rest roughing, spiral finishing, and plunge finishing. So let's have a look at the part. I've picked up a simple part so that we understand what the software is capable of doing, and then I'll quickly show on a complex part. Let me open from the port. Okay, let me delete all these previously created toolpaths. Yeah. And what I'm going to do is, for sake of looking aesthetics or looking better, I would like to take a slice and keep the slice on so that we understand what it's trying to do inside. Okay, let's add a new operation called port machining, roughing, geometry. Again, I have got the geometry saved. It's hardly any geometry is needed for port machining. So I will select all these surfaces as my part surfaces. You can see I've got an undercut, I've got this tube running all through, and it has 2 ends. Each port always has 2 ends. One is the inlet and the other one is the exhaust. And then I'm going to use a spine that I've already generated. Nothing but a center curve, a simple sketch. Now, it's not always essential that you have a spine, but if you're going to work with an open tolerance, it's always better to have a spine. If you're tightening a tolerance, you don't need a spine. Right, you have this. Let's keep an offset of 0.5 millimeters after roughing. Since this is a pretty large part, I also have a large lollipop cutter with me. Remember that in port machining, we only support lollipop cutters, and those are the ones that generally are used in port machining. Levels, we are going to have a cylinder that's going to be parallel to y-axis, and it will pass through a point somewhere here. Okay. In the toolpath parameters, I will have a step over because I'm doing a roughing, so I want to have a step over of 5. And because we are looking at a part in a demo, I'd like to have a step down of about 4 mm. And in the sorting, which is very important because this is new for port, it is asking me, SolidCAM is asking me which side do we'd like to machine, because the port has 2 sides, as I told you before, the top side and the bottom side. This is the top side and you have the bottom side. So it's asking you whether you want to machine the top, bottom, or both. I would like to machine both. And then it's asking me if you'd like to machine both, up to which point do you want to machine both. I have an option of midpoint, or maximum from top, maximum from bottom, or user-defined. I'm going to use user-defined because I would like to show you the rest roughing feature of the port technology of SolidCAM. Whereas from top, I would like to just go to 40%, and from bottom, I would like to go from 60% to 100%. So I have this 20% of area that will relieve in between. The material will be left, and it will be then be handled in rest roughing. All right. tool axis control, you can see there's hardly anything to define. Everything taken care by the system. Link, count check, nothing. Only thing is I would like to increase the tolerance out here because this is a very large part. It looks pretty small, but it's about 500 millimeter. All right. Once we have done this, I'm just going to save and hit the calculate button. Since again it's a large part, take about a minute or so. Okay, it's almost done the calculation, and now it will do the collision checking on either side from top as well as from bottom. Okay, toolpath is calculated. That's pretty quick. Let's simulate this in a wireframe. And this is how the toolpath looks like. You can see it's machined from top to bottom exactly to 40%. It's left the 10% still from top and 10% from bottom. Look at the nice link that it has created on the cylinder passing through y-axis at this point of 200 millimeter. It comes over here and then cuts the part. Now if I run the solid verify, I would not, because it would take some time, but just to show you, let's switch off the holder. You can see what it is doing. Till the time that it can machine, it's doing in 3-axis. And once it starts approaching areas, it starts cutting in 5-axis. All the tilt is done automatically by the system. Because if you remember, in our regular 5-axis machining strategies, you have to define curves and points and all those things and define what kind of a tilt would you need to cut this part, and then that would determine, the angle of the curve would determine how deep your tool would go. All that is out. It's straightforward. Select the surface, select the tool, select the parameters and hit calculate button. Gone all the way up to here. Now it's finished that side, and now it's come automatically on the other side. Now there could be another possibility, because sometimes it is not possible that you use such a long tool right from the beginning. Perfect. You could use a small tool and go only what is possible, and for the rest you could use this technique that I'm going to show you. So if I'm now going to copy this operation, paste it, edit, change this to rest roughing. In the geometry, again I'm going to select the faces, and in the tool axis, in the toolpath parameters in the sorting, I would like to give to midpoint. But before that, I'd like to change it to its original, not that it will do any harm, but I would like to get it to the midpoint, ramp angle of 3 degrees, and step down I could reduce to 3 millimeters just for our sake, so that we could see how it handles the rest roughing, and just hit save and calculate. Oops, it's fine. Save and calculate. Okay, now it's telling me that you need to switch on your stock definition. Okay, stock is automatically updated, so I just have to select and hit calculate. What it is doing now, it's running the stock calculation. It's trying to check what is the previous stock left by the operation. You use that to generate the toolpath for the new rest roughing. Again, since this is doing a dual operation, this could take anywhere between 1 to 1.5 minutes for calculation. I'm doing all the calculations real time in front of you. There are no saved calculations. Of course, I just saved the geometry just to speeden up the whole webinar. All right, it's finished the calculation, and now it's running the, it'll run the collision checks on either side. All right, that's done. Let's check how the host CAD looks like. We'll just quickly check the host CAD. Oops. You can see that why it did all that. If you look at the geometry, there's a difference between the stock that it calculated and the toolpath that it generated. The difference was because of the step down. Now, because of the step down, what it got was it got the cusps of the previous toolpath. So it removed the cusps, and it came to a point where no longer there were cusps. So it created a nice roughing operation out there. So the rest rough works very well even on port geometries. Right, let's quickly run now to the finishing. Let's do the spiral finishing. Geometry again is the same faces. Spine. Tool still remains the same. Sorting, both. Let's give 80 microns again here. And step down is about 3 mm, not 4 mm. Let's go 4. And it's going to do a spiraling of the toolpath. Okay, let's hit save and calculate. You can look at how quickly the toolpaths are being generated. Don't have to wait, don't have to define too many things, and don't have to rerun any operation because you had a wrong result or you did not get a result as you expected. It's very predictable, very accurate results, very powerful. While it's being calculated, let's run through the port. So you have got the new operation, use of lollipop cutters. Port machining strategies, you have got roughing, you've got finishing, and you've got plunge finishing. Generally, plunge finishing is used in those ports where they are very particular about the flow lines appearing on the port area because the gases flow through that. They don't want some kind of spiraling happening inside. So they want the direction of flow of gases also to be followed while cutting. Right. We saw that. These were the machining surfaces, the spine, and if you have to check against any gouge, you can also define check surfaces. Geometry selection, again, as I said, 4 to 5 steps maximum. Geometry selection, tool selection, side step and down step, set area to machine, calculate. 5 steps for roughing. This is the rest rough. If you had the same step over, you would have the same same result. Again, 4 steps. Port finishing, we're going to see now very quickly. We'll see the results. Again, 4 steps. And then you have got the plunge finishing, 4 steps. So anything that you do in these new technologies that SolidCAM has developed is not more than 4 to 5 steps with bare minimum inputs. Right, let's check what's happened to our calculation. It's already done. Let's run the simulation and you can see nice result for finishing. Automatic linking, starting from 1 going to maximum, starting from the other side going down again to the maximum in spiraling. So this was about, in short, for port. Let's look at another technology very quickly, and this is the contour. This is one of the most easiest and nicely developed technologies. The contour is generally used, if I go back to my presentation, it's a robust engineering for engine for machining only curves. You don't need to input any kind of surface. Tool orientation is via tilt lines. It supports different cutters. You could use this application for chamfering or trimming, where this technology could be applied, or deburring a particular edge in 5-axis. So if I quickly run on the part, let me delete this. I need to do some kind of deburring or chamfering on this edge that I'm selecting. And for that, I'm going to use the new contour 5-axis. So I'll add contour 5-axis. Geometry, you can see absolutely no way you can define any surface. Only the drive curve. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. That's it. I need to define the orientation lines, nothing but surface edges. So I have 1 here. There are totally about 10 orientation lines. 2, 3, 4, 5, 6, 7, 8, 9, and 10. All right, so we have the orientation lines defined. We'll just pick the cutter. The tool I'm going to use is a chamfer tool. That's how it looks like. Levels, I'm not going to do any changes except for the plane height. Toolpath parameters, and in the sorting I would like to change the direction of machining to follow curve. That means the way I've selected the curve, it needs to follow all those curves. All right, tool axis also I would not like to change anything except for the tilt. I would like to keep it at 90 degrees to the curve or to the orientation lines, and hit save and calculate. All right, that's done. If you now look at how this would look like, that's how my tool would approach. It will run all along the edge, following the orientation lines. Since we don't have an orientation line exactly at the corner, it did a tilt on the corner quickly. Again, it's going to flow on that edge, move to the next one, rotate itself, and here it goes out. That's it. Very simple. No inputs, much inputs. If I run the solid verify, I've made a pretty tight stock. So if I run it very slowly, it's just enough, very light. You can see, very lightly it has touched the edge to either deburr it or give me a chamfer. Because I've used a chamfering tool, it's given me a chamfer. So this function is pretty useful when you're doing chamfering, when you're doing deburring, or even when you're doing trimming of parts, plastic parts or aerospace parts. When you're doing the trimming, you could use this function. You don't need to have the surface readily available. Most of the times they're not. Right, let's now jump into the last part of our application today. And let me quickly skip this slide. And that's the convert HSM to Sim 5 axis. In this case, I'm going to show you both the options. I'm going to show you the convert to 5 axis, and I also will show you the remaining collisions feature that's been developed in SolidCAM. So let me open up that part. Conversion. I've got a very simple part, so it becomes much more easier. Let's unsuppress our toolpath. So this is a simple 3-axis toolpath that I've generated, constant Z. And what I'm going to do now is I'll edit and define or create a new toolpath for conversion and define my source operation as my previous HSM, a cut tolerance of 10 microns. I'm going to use a source link. The tool remains the same. Of course, I'm now going to check the tool axis is simple tool axis tilted to Z axis, and I've given the tilt angle as 0. However, in my gouge check, I have given an option called tilting tool away with max angle, and look, I have only selected the holder to be checked against these surfaces. That's it. There's nothing else. And what we have new in the 3 to 5 axis conversion, they've got some new parameters when the tool does not fit a certain area, when the tool does fit in a certain area in a short distance, or when the tool does fit a certain area in a long distance. We can define what it has to do. Either it could create 5-axis toolpath but remain close to 3-axis, or 5-axis but be close to a certain angle. So you can now define additional options, additional features into your toolpath. All right, let's go to the levels. Gouge check, and then you have the clearance one. So now the default options are trim colliding and create collision-free links. So let's run the calculation. It's loading the original toolpath, and then it will run the simulation. It will run the collision check. Okay, it's almost done. I'll show you exactly what the remaining collisions mean. So now if I run the simulation, you can see what is happening. As it starts going down, it starts tilting. Well, that's perfectly okay. There's no tilting needed here because it's quite away. But as it goes closer to the wall, once it starts detecting that the holder will start colliding against the part, it starts tilting itself. Okay, this is exactly happening the way I want it to happen, but what are the other things that are happening which I don't want are these jumps. Can you see these jumps? The toolpath has got trimmed itself, it has jumped up. it's probably finding very, very fine collisions between the tool and the part. And that is the reason it's gone to this particular area out here, and it says if there are collisions along the contour of cutting, trim those colliding contours and relink. This is what it did. It just cut the toolpath and relinked it again to make it collision free. And in the link between the two toolpaths, it still found some collisions. So it created new collision free links. So it trimmed, joined it again. If you don't want to see those spikes going up and down, I could keep the collisions on both. Maybe just change the tolerance because it will calculate it quickly. Maybe 50 microns, yes. And run the calculation. You will see that those spikes and jumps will now disappear because they are no longer being trimmed and relinked again. And by the time because we're going to end pretty soon, you could have your questions ready. If you have any questions, put them in the chat area and I'll try and answer each of them to the best of what I know in the new things. And as usual, you're going to have all these parts up on the forum or on the website, Facebook, wherever you want, wherever they generally put. You want to have all of them. All right,
yes,
so the toolpath is ready. Sorry, Eddie, I'm just done. Just a moment. So if you now look at the simulation, all those funny retracts have now disappeared. We've got nothing now with any of these pretty clean toolpaths. So now you know what those options are. All right. Thank you very much for patiently listening because it's pretty long. We've almost taken 90 minutes to show you what's new in this version of SolidCAM in 5-axis simultaneous. And I'm now open for questions.
Yes, Amod, thank you very much. It was very interesting and a pretty long webinar. So I will have some questions here. By the way, meanwhile, our attendees can ask more questions, yes, or you can raise a hand and we will open the line, or you can type your question in the chat area and I will read the question now for Amod. And meanwhile, as I understand, the questions about multi-blade part of the webinar, yes? Okay, so the first question is, if there any difference if we select more than one shroud in geometry selection?
There's absolutely no difference. I mean, you won't see any difference in your result. You would not get any kind of an error. You can still select. But we generally would recommend not to select because the software is very smart. It's very smart in realizing that you have selected a shroud, and what it basically does is internally it creates a revolved surface of that shroud to create the pattern between the shroud and the hub. And the same goes even for hub. For hub, you can look at my pointer, you could have only a 5mm surface protruding out from the edge of the fillet. You don't need more than that. Once it knows that this is the hub, it does the revolve internally. But the only thing that you need to make sure when you're defining a surface for either shroud or hub is that there should be a surface formed from surface of revolution. There can't be some NURBS patch. You might end up into some errors if you are selecting a NURBS patch, but generally they are not because impellers generally are done using a revolved surface. But to answer your question, there would be no difference.
Okay, next question on the last model. I guess it will last model of multi-blade part of the webinar. Yes. you select just half of a hub. Can we select whole hub, or we will get some problems or errors?
So, sorry. Actually, the answer is the same. If it is a surface of revolution, then there is no problem for selecting the entire hub or only a portion of the hub. You will still end up getting the same results, but we do have seen in some multi-blade parts, when you're selecting the entire hub, it does give some kind of an error, but that's also being fixed. It's not a error that's going to remain permanent. Probably in another week, 10 days, that's going to be out. That's very rare, but otherwise you could select the entire hub. You could select all the surfaces that form a part of hub, and SolidCAM would intelligently create a revolved surface internally to treat it as a hub surface.
Okay, next question. What is the best option for 5-axis trimming?
I would suggest you to try the 5x contour, the new 5x contour, because one, it doesn't need surfaces. It can still work just with curves and the orientation lines, which you can pull out from the surface edges itself. It doesn't need special construction geometry. So I would say at the current given scenario, the best bet would be to use 5x contour, the new function.
Okay, they continue this question because they're asking, why they ask this question, because we have incline line option inside Swerve and contour 5-axis. So for trimming, both option looks good.
When you're trimming a part, you use the tip of the cutter. But when you're doing the swerving, you use the side of the cutter. So inherently, both the technologies are different. Swerving is using the side, trimming is using the tip, because you would like to dig into the surface when you're doing trimming. But in swerving, you're actually not digging, but you're only going onto the side. So I would not think that you would like to use swerving to do the trimming. I would still feel that you can still use contour 5-axis to do the trimming, unless you get into situations where contour 5-axis can't really handle that geometry.
Okay, thank you, Ahmad. We have many questions here, requests to receive this presentation, the parts, and all the materials about the webinar. So Ahmad, please.
All will be on the web. All will be on the web. In fact, I started uploading after the first webinar. I reached half, then I had to stop, and I'll start uploading again, and you'll have all the parts.
Yes, because
in fact, I did not show a very nice part because of lack of time. It's another part for port machining. I'll just as you continue talking, Eddie, I'll just show the part.
Yes, because of course we will put it on our reseller forum, so our resellers will have an access. But about the users and prospects, so we will send these parts, these materials to every attendee of this webinar by email. It will be sent from SolidCAM to every attendee of this webinar. But before, Ahmad, please send me all the materials here so I can forward it.
Yes. As you can see, I'm creating a toolpath quickly. Only from the bottom, maximum from the bottom, and parameters, 80 microns, 5, 4. Okay, you can please keep asking me questions, because this generation is not going to take much time.
Okay, so guys, this is the last chance to ask the questions. I see I've answered all the questions. So if you have a question now, just raise a hand if you have a headphone set, or just type your question in the chat area.
Let's see that.
Okay, yes.
Quickly generated.
Mm-hmm.
Okay, I'm done, Eddie. Yeah.
Okay, so that's all. Amod, thank you very much. And of course, we will continue next week with the series of what's new in SolidCAM 2013 webinars. Thank you for attending this webinar. Thank you very much, Amod, again.
Thank you.
And we'll see all of you next week. Goodbye.